All right, it's 12:30 and I think it's about time that we get started. So I'm going to record this lecture so that I can send it to anyone who might miss this particular time. I know we've got people in all sorts of different time zones. So the main thing that I want to discuss and go over today is the midterm 2. So I hope that you have all received my email with the several bullet points. So it's basically become clear to me as I graded this that this exam was too challenging. I had some tricky problems, and it also looked like it was probably too long. I think a lot of people had or felt some time pressure. Um, and uh, the scores averaging around 50% means that I've got to do something to rectify this, and if I can, try to make some improvements in teaching to make sure that I'm, well, okay, so partially on the test, maybe also partially on my teaching. So that's something that I want to work on. So as I described, the thing that I was thinking of doing in this situation is offering you a chance to win back half of the missing points that you missed on the exam by reworking through these problems and sending them to me as a file. And if they're correct, then I'll look it over and give you back half the points. This should provide you with a way to have a more reasonable sense of what your grade looks like. But it also hopefully will have you go over some of these problems again, because while I take most of the responsibility for making this exam too hard, there were a couple problems where people in general did pretty poorly, and poorly in the sense of not even perhaps knowing where to start or having some kind of important misconceptions about how the proof should go. Is that more or less clear? Does anyone have a question on that part of this? Seems like there are a few questions. Yeah, honestly, what I want to say is try not to stress out about this too much. This was too difficult of a test on my part, and getting the option to get half of the missing points back is one part in trying to rectify this and get a more standard grade. So yeah, that's what I want to kind of say about this. Don't get too stressed about the raw numbers that you see on the test. Okay, so what I'm going to do with the rest of this lecture is essentially go through the problems and discuss them. And even if I don't write down the full proof, since I'm going to be asking you to write down the full proof, I want to at least discuss the mathematics of the proof, so that the only thing that you need to, the extra work that you need to put in if you want to hand this back to me and gain points back is to format it into a very nice proof. And of course, you're welcome to ask questions as I go along. Yeah. Any questions? It's not very many responses. Okay, if no one's gonna ask questions, oh, has the test been uploaded yet? Yes, so what I've done, so I graded the test by hand over spring break and a little bit after spring break. And then I realized that I wouldn't be permitted to hand back the tests to you. And I lost access to the scanner in the department. So what I did is I took pictures by hand of every sheet and uploaded those documents and packets to Gradescope. And so how you'll be able to access and interact with your exam is via Gradescope. If you didn't sign up for Gradescope by say 11:30 today, then your test is on Gradescope, but it hasn't been matched with your profile on Gradescope. So what I would say is, if you haven't logged on to Gradescope and gotten in with the code that I sent on Sakai, then do so. And if by this afternoon you still aren't matched with your test, then email me and I'll make sure that you can see it and yeah, ask questions. Is that? Yeah, sure. Any other questions before I get started on the math? And is the audio and video clear? Is that of okay quality? Cool, thank you. Great. How will the next midterm be structured is an excellent question. I would say that I hope to have an answer on that question to you by Friday or Monday at the very latest. Basically, no one in our department knows how we're going to do these tests. What I will probably end up doing is, in some form, making a test on Sakai, which you have, say, 24 hours to take, because we have people in all sorts of different time zones. And so you'll have 24 hours, and then when you click the start button on Sakai, then you'll have like an hour to take the test, and then when time's up, it'll just kind of submit what you've done to me. And there might be more, people are bandying around different anti-cheating measures, and I don't know how we're going to, how to work through it. So basically, how we're going to test is the, I think, hardest question that remains for me. I believe so. I'll have to check. I did match a number of tests to people, so it's my impression that if you logged on to Gradescope and you signed into the class with the code, then you should be able to view your test. If that's not correct, then let me know and I'll do what I need to do after this session. Still can't see it. Okay, so it seems as though people cannot see their test on Gradescope, so what I need to do is deal with that after this class. So I'll do that. And yes, in general, I still intend for partial credit to be granted on the Sakai test. Once again, it's kind of difficult for me to see how I'll do that. I don't want to make a multiple choice. This is a proofs class. I don't know if I can ask you to type in proofs. So this is what I need to work on today and tomorrow. Yeah, it's really rough. So yeah, I'll try to find something. Yeah, and then after this, I'll go make sure that you can all actually see your exams. Any further questions? And once again, yeah, I know that the situation has kind of catastrophically damaged our ability to have class. The Gradescope code is on the Sakai assignments, and if you can't find it, I can also send you an email with it, but it should be found on Sakai assignments, yeah. Okay. That is probably the most helpful thing to do, yes. Okay. So with all that being said and done, let me start going through the actual problems of the test. I want to kind of discuss some of the major pitfalls and things like that. Okay, the first one was, on the whole, pretty devastating. So the first one is saying prove that between every rational and irrational number, there is an irrational number. Okay, so what do I want to say about this before I launch into the actual mathematics? Here's one. There are perhaps two very important comments. One is that this can't be proven by example. Example or counterexample doesn't work here. Right. Example and counterexample doesn't work here, or at least the only methods that I know of using an example, say involving the square root of 2, are really contrived and really difficult and probably couldn't be written in the piece of paper that I gave you. So a lot of people tried to use examples about finding irrational numbers between 1 and square root of 2 or something like that. And in general, those just won't work. Two is that a lot of people also try to use some sort of density argument, using things like there being infinitely many rational numbers or infinitely many irrational numbers. Those also don't really help here. Infinitely many rationals or irrationals. Like these ideas that I discussed about cardinality, they don't help us very much. So these were some common pitfalls that I saw. This proof is going to be a straightforward, more or less direct proof. And if I have to prove that between every rational and irrational number there is an irrational number, then my proof should start off by being, let x be a rational number and let y be an arbitrary irrational number. You can't pin them down, you can't pick examples, you can't let one be square root of 2. You just have to say, if I'm proving this for two arbitrary numbers, take any rational number and take any irrational number. Okay, so I'm going to, since everything's being recorded, you can go back and read these things again. How this proof should start. Pick x rational and y irrational. Right? I don't have any control. The Gradescope code is right above. It's, yeah, there we go. So we pick x rational and we pick y irrational, and we have no control over which rational or which irrational number we pick. Now, the next thing that we need to do is to find some number in between these two numbers. What's a way that given two different numbers, we can find a number in between those two numbers? Anyone have an idea? So maybe this was the tricky part of, yeah, exactly. Take the average. Let's take the average of these two numbers. The average, which is going to be, so examine the average, which is going to be x plus y over 2. Since x can't equal y, why can x not equal y? Because one's irrational and one's irrational. Since x cannot equal y, we see that x is less than x plus y over 2, which is less than, or sorry, it's not true that we know that x is less than y. So either x is less than x plus y over 2 less than y, or y is less than x plus y over 2 is less than x, right? This is the case when x is less than y. This is the case when y is less than x. And then the last thing that we need to show is that this number that we've produced actually has to be irrational, right? Claim x plus y over 2 is irrational. And perhaps this is the step that I will let you argue on your own. If you missed this, I'll just say verbally what you'll need to show. One, you'll need to show, so here, you should say x plus y over 2 is equal to x over 2 plus y over 2. You should show first that y over 2 is irrational, and then you should show that the sum of an irrational number and a rational number is irrational. And then you'll have shown that this number, whatever it is an irrational number, and it also lies in between x and y. Right, so maybe the tricky step here was thinking of the average as a way to find some number in between two arbitrary numbers. Not very many people tried something with an average, but that's an easy way to proceed with this problem. Any questions on this collection of ideas? Once again, something to emphasize is the way that we would start off this problem is by taking an arbitrary rational number and an arbitrary irrational number. We don't get to pick, we can't do anything involving square root of 2 or things like that. Just an arbitrary rational and an arbitrary irrational. Is that okay? No one is making any, oh, okay, great. I'm happy. Cool. And if this is clear, this is good. This is a way to, yeah. Yep, to help. So just to clarify. I'll erase this and prepare the next problem. And then if anyone has any questions, I'll address them. Yeah, so the final step is we've produced some number which is in between. And indeed, these two cases are pretty much the same. You can do this without loss of generality because the number that you're proving to be in the middle doesn't change either way. So you don't actually need to do both of these cases. You can just say without loss of generality, let x be less than y. When x is greater than y, then you're still going to be dealing with the same number. So these two cases really are one mathematical step. And then here, the two steps that I would recommend are first showing pretty easily that y divided by 2 is irrational. So you want to show that this number is irrational. The way that I would do it is first I'd show that y over 2 is irrational, and then I would prove that irrational plus irrational is irrational. Therefore, this number is irrational. Is that okay? Cool. I hope you're all taking care of yourselves, by the way. It seems like things are getting very serious. Okay, so the next problem, 2. Let's talk about this one. 2. So this is the following. Prove or disprove that if A B and C are non-empty. And A cross B is equal to A cross C, then B equals to C. Okay. Yeah, I think we're going to go into shelter into place pretty soon here in Orange County. Let me first make some remarks about things that I saw that I didn't like on this problem. Here's one. It's always a good idea to try to work out an example. And so I very much encourage, if on some scratch work or off to the side, you actually wrote out some sets like A is equal to, I don't know, 2, 3, and B is equal to whatever, I don't know. Because that helps you, and it helps you figure out exactly what the structure of this problem is, right? Just as a brief reminder, like, well, should I write down some example of a cross product of sets? I can if you'd like. But here's something that is not correct. Some people wrote things like A is equal to the set like this, A0, A1, A2, etc. B is equal to some set B0, B1, B2, etc. Can anyone tell me what's wrong with this way of starting out, of writing these sets? Anyone? It's related to that, yes. The point is, writing things out and giving them integer numbers like this implies that this set is countable. Writing something like this says, well, maybe it goes off in this direction, maybe it goes off in this direction, maybe it's finite, but listing them out like this says I'm putting all of them in a line, one after the other, and that's countable. But the real numbers are, if A is equal to R, the real numbers are never countable. I proved this in class. So there is no way to ever write R such that some segment of it looks like you're ordering them on a list and you'll eventually hit all of them either by going this way or by going this way. So it's related to the fact that in general, I can't pretend that a set could look like even an infinite list on both sides. If A is R, that's already right out the door. So all I can really say is that these are just sets. A has some elements, B has some elements. Okay. Another thing that frustrated me, well, okay. I'll say this. There are a couple points that I want you to take away from some of these problems. And one thing that I feel like I repeated in class, but maybe I didn't emphasize it enough, is that when you're trying to prove an equality of sets, and here we're going to be thinking about an equality of sets, we want to talk about double inclusions. We want to start with some elements in B and show that it's in C, and vice versa, start with an element in C and show that it's in B. And one is there are other ways of proving this. Well, not, what should I say? There are clever ways of proving this that seem like they get around this, but far too few people started off this proof by saying, let B in B. The most basic and straightforward way of proving this statement starts with take an element in B, I want to show that it's in C, and then I'll do the reverse. And very few people had that kind of basic idea of how do I work with set equality. Okay, it turns out that this statement is true and we can prove it. And it starts off this way. Okay, so the proof, I start off by saying, let B be in B. Since A is not equal to 0, or since A is non-empty, what does that imply? What does it mean if A is non-empty? It can be mapped. Yeah, I would say since A is non-empty, there exists some element. There exists A in A. So the point is, since A is non-empty, I can produce some element. It's not equal to the empty set, I can produce an element. If I have an element of B and an element of A, what does that produce? Or what can I get from those two? Tuples, exactly. I can get A comma B inside A cross B. Perfect. Thus, the tuple AB is inside the set A cross B. Very good. Now, since A cross B is equal to A cross C, what does that mean? Yes, exactly. Then the tuple A comma B also has to be inside this set, A cross C. But A cross C is precisely the set of tuples such that A, the first coordinate is in A, and the second coordinate is in B. Thus, B is inside C. So what I've done is I've proven 1/2 of the double inclusion. For any elements B and B, by A being non-empty, I produce an element in here. It has to be an element in here, thus B is in C. And then the other direction follows as above. Nothing. So this is essentially me saying, without loss of generality, start with something in B. If I started with something in C, I'd do the exact same process, just in reverse. Okay. So once again, what I want to emphasize here is that I'm trying to understand an equality of sets, so I should think about double inclusions. I should think, let me take an element in B and show it's in C, or let me take an element in C and show that it's in B. Okay. Let's see. Yes, exactly. Exactly. If I were to write out the, so thus B is contained in C. If I wanted to show C is contained in B, we use the same argument. Thus, B is equal to C since we have a double containment. Okay. Is that all right? Here's one further question. Is this true if we permit some of the sets to be empty? So my question is, the following. What if I say prove or disprove, and then I remove this condition that A, B, and C are non-empty sets? What if I just say prove or disprove that A cross B is equal to A cross C implies B cross C? Does anything change if I remove this condition? You can cross the empty set with the empty set, yes. And indeed, the idea is if I remove this condition, then the empty set will play an important role, and this statement will actually be false in this generality. And I can give you an example. So if we take A is equal to the empty set, B is equal to Q, the rationals, and C is equal to R, then A cross B, what's the empty set cross the rationals? So the empty set cross anything is just going to be the empty set, right? Because to understand the cross product, you need to take an element of set A and an element of set B, but there are no elements of set A. So A cross B is equal to the empty set, and so is B cross C, or A cross C is equal to A cross C. Anytime that I cross something with the empty set, I get the empty set. But B is not equal to C in this case. So I'm just pointing out that this assumption that A, B, and C are non-empty is required. If I remove this assumption, then the statement is false. If I add this assumption back in, then it's true. That's right, exactly. If A is the empty set, B and C can be arbitrary sets, and then these two will always be the empty set, but then B and C are not linked in any way. In other words, I'm saying that an important part of the proof is I started with a B in B, and then I needed an A in A, so that I could then make the tuple A comma B inside A cross B. If there's no element A, then this argument doesn't work. So this is just kind of a further exploration of this particular problem. The non-empty restriction only has to be on A, right? Let me think. So if A is non-empty, then it's probably, yeah, I think that is the case. If A is non-empty, then if one of them is the empty and the other one isn't, then the cross product won't be equal. Yeah, it's my impression that the non-empty restriction really only matters for A. Yeah. Okay, any further questions on this one? Okay, let me erase and start doing the next one. Okay, the next one is the following. Just one second. Okay. We have A inside some universal set, U. Show that if A closure is contained inside A, then A is equal to U. Okay. So again here, what I would want to, so there are some slick proofs of this. For instance, there's one proof which says, assume for the sake of contradiction that A is not equal to U, and then you derive a pretty quick contradiction. I'll go over that proof because it's nice. But once again, what I want to reinforce here is that we're proving an equality of sets. So the first thing that should be in our mind, once again, is a double inclusion. One inclusion is obvious, right? U is the universal set, so A has to be contained inside U. So proof, double inclusion, because we're trying to prove an equality of sets. We already know that A is a subset of U. That's just given to us. A is a subset of U. So what we want to show that U is contained inside A. And essentially we'll do this by contradiction. Proof by contradiction. Assume, so what does it mean to contradict the statement that U is contained in A? It means that there must be some element in U which is not in A. Then assume there exists a U in U such that U is not in A. Now, what do we know about universal sets? What do we always do when we have a subset of a universal set? Yeah, we think about complements. What a universal set allows us to do is take a complement. In particular, we know the following thing about complements. Then A bar, sorry, not cross, A bar union A is equal to the universal set, right? If U is not in A, then by definition, U is inside A bar, right? A bar is the collection of all elements in U which are not in A. But A bar is contained in A. Since A bar is contained in A, U is inside A. This is a contradiction. I started off by assuming there existed an element that was not in A, and then I was able to show, using my remaining assumptions, that it's in A. That's a contradiction. And essentially this is, yeah, this proof right here, what it does is it does two things. One is that I wanted to bring out the idea that you should start, at the very least, you should start your thinking about these problems by trying a double inclusion. If you try a double inclusion, then you'll find, you'll make some progress. Okay. The premise of this question messed me up. What does it even mean to say that the complement of A is a subset of A? Right. Okay. So here's how I can address that question. That's a very good question. The point is, here's the point. The point. The empty set is always a subset of any subset for any A. Right? The empty subset is a subset of A for any A. What this condition is saying is that if A bar is a subset of A, then A bar has to be the empty set. Because if it has any elements, then it's a contradiction. I think that's exactly what you're describing in your question. What does it even mean to say that the complement of A is a subset of A? The point is, no element can be both inside the complement of A and inside A. But there is a set, namely the empty set, that is as a subset is contained in A, right? The empty subset would satisfy this condition. And of course, if A bar is equal to the empty set, then A is equal to the universal set. Yeah. So several things to kind of drive home here is that I think a lot of people were kind of confused by this, right? It looks very wrong, and you're right to think that it looks very wrong. If you assume this, the thing that you have to remember is that the empty set is a valid subset of any set. And so in particular, the point of this problem was to show A bar has to be empty, therefore A is the universal set. And the second thing that I want to reinforce again is that it's a good idea, and you should start off proofs about set containment by trying a double equality or a double containment. Pick an element of A, show that it's in U. That's obvious. Pick an element of U, show that it's in A. Well, what goes wrong if it's not in A? And we butt up against this other condition. If it's not in A, it's in A bar, but then it's in A again. Contradiction. You've broken something. Any other questions on this one? So, I mean, that's essentially what this proof did, right? What I showed is that if A bar is not the empty, right? When I assume exists U in U such that U is not in A, this assumption is equivalent to A bar is not empty. And then I showed the statement A bar is not empty leads to a contradiction. If A bar is not empty, there's an element in here. By assumption, it's an element in here, and you can't have an element that is both in A and A bar. It's not really another way. It looks a little different. Like there are different ways to write this proof, but they fall back on the same idea. Any other questions? And again, don't be too frustrated by this stuff. I know that, I mean, this is my experience with a lot of math classes of this flavor, like discrete math, linear algebra, a lot of algebra. When someone writes down the proof, you feel like you understand it very well, right? And I'm sure that when someone talks through it, you understand all the steps and it seems clear. And it's just true that when you're faced with these questions with no support, they become harder in ways that are kind of hard to quantify. And so don't be too worried necessarily. If you understood these steps, then it's just a question of practice. So don't stress out too much. Okay, are we ready to move on to question 4? Great. Okay, question 4. Essentially here, all I was asking for was the picture. So show that z greater than 0, sorry, not greater than or equal to, z greater than 0 cross z greater than 0 is countable. A first step, and so the way that I graded this problem is in these 4 steps. First, did you write down the right elements of this set? So that's kind of a first thing to look for when you think about this. You should just write down what are some elements in here. The elements in here are all tuples such that they're both positive integers. So I can start writing down some elements. Well, 1, 1 is the first element in here, right? There's nothing smaller than that in any way of, well, not in any way, but it's reasonable to understand this as some first element. And then there are other elements that look like, I don't know, 2, 3. There's one that looks like 1, 7. There's one that looks like 1,000 or 100, and then 17, right? Okay, there are a bunch of things here. The first is getting the elements of the set, right? And the next is to remember that actually this looks, or at least I can arrange these elements on a grid in a very similar way to the way that I arranged the rational numbers on a grid. For the rational numbers, I did something like 1 over 1, 2 over 1, 3 over 1, 4 over 1, so on and so forth. 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And I can do a very similar thing here. These are essentially coordinates of the positive right quarter plane, right? I'll do them down, but you could arrange this in many ways. So here's one way to arrange these numbers: 1, 1, 2, 1, 3, 1, 4, 1, and so on and so forth. Then 1, 2, 2, 2, 3, 2, 4, 2, etc. Or you could literally arrange these on a grid, right? Like this is the point 1, 1. This is the point 1, 2. This is the point 1, 3. There are a bunch of ways of organizing these. 2, 1. This is the point 2, 2. This is the point 2, 3. Whatever, it doesn't matter. A lot of ways to organize these numbers, but the point is you want to organize them in one of these kind of infinite squares where it's extending infinitely in 2 directions, right? So the next one is going to be 1, 3, 2, 3, 3, 3, 4, 3, and so on and so forth. And then once you're here, you just remember the argument that we used to show the rationals were countable. For the rationals, we had to skip numbers, right? Because for the rationals, there were many representatives. If I view, like each of these pairs, I can turn into a rational number by having the first number be a numerator and the second one be a denominator. And if I do that, then 1 over 1 is the same number as 2 over 2, is the same number as 3 over 3, etc. This is actually easier than the rationals because all these are different. The way to show that these are countable is just to snake exactly through them, not skipping anything, just hitting all of them in this procedure. So this is the picture that I was looking for this problem. Some mistakes that I saw, some people got as far as writing down the numbers in this order, for which I gave, I think, half credit. But then they started doing some different patterns. For instance, saying, I'm going to start by counting this one, and then I'm going to count this one, and then I'm going to count this one, ... and then I'm going to count this one, and then I'm going to count this one. And this, for instance, doesn't work really because this set is also countable, right? So in order for this to be valid, you have to tell me at what point you stop counting on this line and you start counting on this line. And then if you cycle through that a couple times, then you have to tell me when you stop that process and you start the blocks over here. So what I'm saying is that there are ways to try to link all these numbers together that don't hit everything, or at least it's not clear that they don't hit everything. There are other options than the one that I wrote up. One example, for instance, of another valid approach, one that I don't recommend, but I'm just showing you that there are other valid things out there, is to count in blocks. Like I could count this one, this one, this one, and this be, you know, block 1. Then this could be block 2, and I count this one, this one, this one, this one. Then this could be block 3, 2, 4, right? And then I count this way, this way, this way. But then you see I'm just making a bigger kind of snake, what's up, Luis, out of these semi-blocks. So I probably shouldn't even have brought up other ways that are valid. The point that I want you to remember about this is you should be snaking through these numbers along diagonals, all of the diagonals of which are finite. So if you want to, just forget what I just said. It's possibly for the best. And just remember the picture of. Is that okay? Yeah. So what that would, so it's nearly there. What you then need to assert, which is something that we proved in class, is that if you show that z cross z is countable, which your spiral did work, it does show that z cross z is countable. But then you still want to show that z greater than 0 cross z greater than 0 is countable. So the next step would be to show that a subset of a countable set is countable. And I proved that in class. But for your proof to be complete, you would need to prove that as well. So I found some bigger set, I showed that's countable, and then if you show, and it is a true fact that a subset of a countable set is countable, but you'd have to prove that on a test. Yeah. So the spiral outward is a valid way for z cross z, and it is the first 2/3 of a valid proof for z greater than 0 cross z greater than 0. Any other questions? Yeah, that's right. The things that I was looking for a complete proof are drawing the picture and then expressing exactly how you would zigzag. And you know, there's more to say here, right? Like on some level, one should justify why this is a surjective function from the positive integers to this whole set. But yeah, I gave full credit for this, like literally this, I gave full credit for, I think. Despite maybe wanting a little more, but yeah. Cool. I'll erase, and then if anyone has further questions on this one, I can answer them. How are we doing on time? We're doing all right? We're doing all right. We're doing just fine on time. Okay, moving on to 6. 6 was unfortunate in the following way. So what was 6? Oh, 5? 5, yes, 5. Forgive me, 5. 5. 5 was unfortunate in the following way. Find both I is equal to 1 up to infinity, ai, and intersection I is equal to 1 to infinity of ai, where ai is equal to 0 up to I, and then ai is equal to I to infinity. Okay. What is this set? From 0 to I. So this one's partially my fault. This is not how we write integers. This bracket notation is how we denote the set of real numbers between 0 and I, not inclusive. And many people were interpreting these things more or less correctly, except that they were saying it's only the integers inside these sets. But this is the set of all real numbers between 0 and I. So when I is equal to 1, there are infinitely many things inside this set. So a lot of people got tripped up on that, and I have to take partial responsibility. I mean, I went over what these sets are, but very briefly. And it's true that we've been working mostly with integers. Right, so that was one common error here. Okay, now let me let me first draw some of the sets that I'm thinking. Let me first draw these a couple of these sets between 0 and I. And I think that drawing just some examples would have helped a lot of people on this one. Some examples would have been good. So here's my number line. Yes? Does someone have an actual question? Is someone actually going to talk to me? Holy cow. No. No one's going to talk to me. Okay. Okay. Let's do the first set. Oh, let me actually make my number line. So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, say. Okay. So A1, A sub 1 is the interval between 0 and 1. So this is A1 right here. A1. Yes. This set right here, all these numbers in between 0 and 2 not inclusive, is A2. Put some fancy colors down here. Oh, no, that's the wrong fancy color. Oh, I've just broken my, okay, whatever. This lime from, this is probably invisible to you. Is this visible at all? Okay, this is A3. And so on and so forth. Is the lime visible? Someone kind of, okay, let me make it in a different color. But anyways, you get the point. The point is I'm doing intervals on the number line that don't include the end points. Is that better? Yeah, I'd be nicer with chalk. Okay, so with this in mind, what is the union of all of these sets? Remember, the union is anything that is inside any of these sets. The union is going to be, well, the union of these three is indeed 0 to 3, but if I let the i's go to infinity, it's going to be the positive reals. Not all of r exactly, but it's going to be r greater than 0. So the union from I is equal to 1 all the way up to infinity of 0, comma I is equal to R greater than 0, right? Every single number that is bigger than 0 lies somewhere on this number line to the right of 0, and it lies less than some integer, so it'll eventually be inside one of these sets A, I, right? Like, think about 101.5. That's going to be inside A sub 102, and inside A sub 103, and inside A sub 100,000. So the union of all these sets is R greater than 0. And then, exactly as Susan has said, the intersection of these sets is what is inside every single one of these sets. And indeed, all of these sets contain the interval from 0 to 1, right? All these sets are nested. A1 is inside A2, A2 is inside A3, A3 is inside A4, et cetera, et cetera. When I take the intersection, I'm looking for all the elements that are in all of the sets, but that's precisely going to be A1. The intersection of I is equal to 1 all the way up to infinity of 0, I is exactly equal to 0, 1. Okay. Any question on this? We just did the first piece. Any question about why the union is what it is or the intersection is what it is? Yeah, you could also write the union, this thing, R greater than 0, this is also equal to 0 to infinity. We're allowed to use this open brace of infinity to denote the fact that it is unbounded above. It's an interval which is unbounded above. So that would also be valid notation, yes. And are we okay on the intersection? Okay, so now let's discuss the other set. And once again, I'm going to use the number line. Now the sets look quite different. Now let me draw the first couple ones. So now I'm taking the closed interval containing 1 and going off to infinity. So A1 is everything to the right of this, so A1. A2 is everything to the right, including 2. A3 is everything to the right, including 3. A4, oh no, I've messed up my green. A4 is everything to the right, including 4. So we kind of have the opposite sort of behavior. With this set, every set is included inside the next one. In this set, everyone is included inside the previous one, right? A4 is inside A3, A3 is inside A2, A2 is inside A1. Okay? So what is the union of all these sets? Well, since they're all included, you just have to take the one which includes every other set. So here, the union from I is equal to 1 up to infinity of the I comma infinities is exactly equal to 1 comma infinity. Everything else is inside here. So just take the biggest one. And now what is the intersection as I is equal to 1 all the way up to infinity? I infinity, can anyone tell me? The empty set, exactly. This one will be the empty set because if I take any element in any of these sets, say I take an element in A3, like if I want something to live in the intersection, it needs to live in everything. So in particular, it'll live in A3. But any number in A3 is less than some integer. And so once I get up, like if let's say I guess that 500.2 is inside everything. Well, it's not inside a sub 600, right? So any number that you could pick is less than some integer. So any number, any b inside R is less than some k in Z, and then b is not inside a sub k, which is equal to k all the way up to infinity. You didn't need to explain all this to me. I just accepted empty set, but that's the idea behind it. So these two pairs kind of behave differently. One, the sets kind of grew and they were nested inside, and the other ones, the sets shrink and they were nested inside each other, but in the opposite way, where A3 is inside A2, A2 is inside A1. Any questions? Any further questions, or is this okay? Okay, let's do the last two. The next one is the injective one. I think this one was okay. I think that there weren't too many. Well, actually, I graded this like a week ago, so I totally forget. Okay, almost there. I know that it's been a long class time. Okay, so so we've got sets A. I'm just going to write it out this way. F maps from A to B, and G maps from B to C. So if G composed with F is injective, then F must be injective. Okay. So, I remember some issues that I had here. One is that these pictures where I draw arrows in here, things like this, these are not proofs. They can give you ideas about the proof, but this in and itself, if you drew pictures and used these essentially in your proof, then you had to lose some amount of points. These should be how you build your intuition and how you try to think about these things with some examples, but these do not consist of, the proof doesn't involve figures like these explicitly. Okay, that's the first thing that I want to say here. Okay, and the way that I prove this is I prove this by contradiction. Okay, so assume, for the sake of contradiction, that F is not injective, but G composed with F is injective. What does it mean if F is not injective? Someone should write something in the chat. Yep, not one-to-one, which means, so it's not quite one input has many outputs, but rather many inputs have one output. So the picture, and again, this is not part of the proof. The picture for something not being injective is that several different inputs go to one output. So it's still a function. So this is the picture, but it's not part of the proof. If I assume that F is not injective, then what I can say is, thus, there exist x1 and x2 inside A, x1 not equal to x2. I pick two different elements, and then f maps both of those elements to the same thing. And f of x1 is equal to f of x2. Right? That's what it means for f to not be injective. It takes two different elements and sends them to the same thing. We can call this B in B equals B in B. Okay? But now I claim that this prevents G composed with F from being injective, right? Now examine G composed with F of x1 and G composed with F of x2. G composed with F of x1, this is equal to G of F of x1, which is equal to G of B. I just called these two elements, whatever they are, they're equal to B in here. This thing over here is also equal to G of F of x2, but x2, F of x2 is also B. So this thing is also equal to G of B. And G of B is equal to G of B, right? I have a function, I give it some input, it gives me a well-defined output. But this means that G composed with F is not injective. So G composed with F is not injective, right? Because I took the input x1 of G composed with F, and it got me whatever this number is. And then I took the input x2, let's call this equal to C. This is equal to some C inside here. And then if I plug in x2 into the function f composed with G, then it goes to the same place. But x1 and x2 are assumed to be different. So G composed with F is not injective. Contradiction. Okay. Now, so I understand that what I'm saying right now might sound frustrating. What I'm going to say is the pictures are not a proof. Can this only be proved by contradiction? Yeah, I believe so. Yep. Not a direct proof. To prove this directly, you would need to examine every single possible pair of functions on sets, right? I only see a way to prove this by contradiction. So I've repeated many times that the picture is not part of the proof, and that's true. The picture is not part of the proof, but the picture is very important for the intuition behind the proof. So this is the proof. When you write it up, you should make it a little neater and be a little more careful. I'm just outlining it. But this is the mathematical language of the proof. And now I'm going to draw the picture, which is for your intuition. The picture is for intuition. So the picture is very valuable, just not part of the proof. The picture is as follows. If I have three sets and so here is F and here is G, and I've got some stuff going on here. Who knows what? And let's say that I've got some function which goes like this. I don't know. I'm just making something up here. Say that. Or maybe let's make them two different things. So G is injective, but let's make F not injective. That's what I want. The thing to remember is that the composition of functions looks like you follow the arrows all the way through, right? So the whole point is that if f is not injective, then the composition of the functions can't be injective, and the picture is this one. This two things map to the same thing here, and then by a function they map to the same thing over here. So here, the g composed with f starts here and goes here, and it takes this point, starts here, goes here, and ends up here as well. So the thing that, like, g composed with f can never be injective if f is not injective, because just examine whatever g does to this point where the two inputs are mapped to the same output. G has to map this thing to one thing, and then you're no longer possibly injective on the composition. This is the picture, or this is one picture that is associated to the proof that I did above. Is this helpful? Is this visible, first of all? Okay, yeah. So the picture is very important for you to kind of sketch out and work out what's kind of going on with this problem, and then you leave it behind when you write up the formal proof. But the picture is still important. Okay, we're almost done. Last one, yeah? Oh, we're over time. If you want to leave, of course, you could leave at any point because this is all being recorded. But let's do the last one. This one wasn't worth very many points because there's not much bookwork in it. I just discussed it in class. This is asking for the cardinality of the set of functions f from the empty set to A and say G from A to the empty set. Okay, first, let's count where A is not empty, A not equal to the empty set. Let's count functions from the empty set to A. How should we think about functions, especially when we're dealing with things like the empty set? A function is a relation and a relation means some subset of the cross product of these sets. A relation on empty set cross A, which is equal to the empty set. So it's a subset of the empty set. Yeah, mapping one set to another, you're absolutely right. You're absolutely right. So this is kind of an extreme case. In every other case, when you're not dealing with empty sets, a function maps an element of here to an element of here. So everything that you are writing is correct, except that that point of view doesn't help you interpret this one weird case where I'm talking about the empty set mapping to A. So you're not wrong. And this question is kind of mean because this is a weird side case, but we did discuss it. So it's a function's relation on here, which is the same thing as a subset of the cross product. So what are the possible subsets of the empty set? The only subset of the empty set is the empty set. And then there are two things to check. For a relation to be a function, you need two more things. One is for every A in A, there exists a B in B such that f of A is equal to B. This is the condition that your function maps an element of A to an element of B. So this is exactly what you two are saying. And then part 2 is that if f of A is equal to B1 and f of A is equal to B2, then B1 is equal to B2. And then the empty set satisfies both of these conditions because there are no elements in A. So this is vacuously true. There are no elements in A, so this situation never occurs because there are no elements being mapped anywhere. All this is to say that there exists a unique function from the empty set to A, which is just the relation, the empty set contained inside the empty set, and this satisfies these properties. So, am I okay to erase this? I'm sure I am because I'll record this and you can pause it and look more carefully and all that. But the point is that the size of functions from the empty set to A is equal to 1. There's exactly 1. And it's that, and what this is this is the subset called the empty set of the empty set. Okay, 2. Let's look at functions, size of functions from A to the empty set. And remember, A here is not the empty set. Okay, so what is the first thing that we check for a function is that it's a relation. So I'm looking for a subsets of A cross the empty set, which is equal to the empty set. Once again, the empty set is the only subset of the empty set. But now I have to check that it satisfies the relations. One, that for all A in A, essentially we need a tuple. We need f of A is equal to B, or A comma B is inside the relation R. Well, if A is non-empty, there are elements in A, and there are no tuples like this because the relation is just the empty set. So in this case, the empty set contained inside the empty set doesn't satisfy this first extra condition, which is elements have to be mapped somewhere. Here, there are elements, they must be mapped somewhere. In the previous case, there were no elements, so it was vacuously true that they were mapped somewhere. Here, there are elements, and there's nowhere to map them to, so this can't be a function. So there are no functions from a non-trivial set to the empty set. And the size of functions from A to the empty set, now this is equal to 0. There are none of them. There's no relation that satisfies all the things that you need it to satisfy to be a function. This one was tricky and kind of mean, but I only made it worth 2 points. Hopefully that's some help. And for the answer, I just accepted, like, if you just wrote this, that's good. If you write this, that's enough. Okay, wow, I've talked for a long time. It's been nearly an hour and a half. If anyone, oh, how many points was the whole thing out of? The whole thing was out of 28 points. Yeah, and I also want to, I'm not going to apologize for testing in general, but I do feel bad that this test was too long and had too many challenging problems. I don't want to add more stress onto you. So I hope that with my explanations, things feel kind of clear, and I hope that you take advantage of the ability to gain points back. And please chat with me. I'll try to figure out what I need to do to make your tests visible to you on Gradescope. Chat with me, talk to me about stuff. I'm very happy to do that. One of my other office hours, so currently I these are my office hours / recitation times. Just send me an email if you want to talk individually, and we'll find a time to talk individually. Are the lecture videos still doing okay? The 2 lecture videos. So I didn't get to really talk about the material on modular arithmetic. So let's try to at least discuss when can we make up points. So here's the system, and I think it's explained in the email. Once you know which problems you got points off on, if you write down correct proofs for those problems, I will give you back half of the missed points. So what I would say is send me some document via email where you write down full proofs of all of the problems where you possibly missed. And if all of that is correct, then I will give you back half of the points that you missed. Send that stuff to me before the next exam. I'm happy to continue answering questions.
Okay, I'm gonna come off mute because I don't want to type anymore.
Sure.
I'm just a little confused about how G composed of F, if G is injective, why it matters whether F is injective. So it's about like the original input, not the.
Yes.
Okay.
Yes, exactly. So in this case, I can explain this to you with an example. Let me write out very explicitly these functions. Okay. Here is my set C, here's my set B. G is going to go in between these. And I'm going to make this be B, and I'm going to make G be injective. You agree that G is injective?
Yes.
Okay, great. Now I'm going to make another set called A, and I'm going to make, and so I'm going to have some function f in between these, and I'm going to make it so that f is not injective. For the homework and corrections, would you prefer it written or typed in LaTeX? Either, it doesn't matter to me. I would prefer LaTeX, and I would encourage everyone who wants to play around with LaTeX to use it because it's great, but that's not something that I ask of you, so it doesn't matter. Okay, and now let's make f a function which is not injective. Let's do it by, say, taking 2 points and sending them both to the same place, right? So now I've set up a G is injective, F is not injective. Let's give numbers to all of these. Let's say this is 1, 2, 3. Let's say this is A and B, and let's say this is, I don't know, A, B, C, 1, 2, 3, do, re, mi, do, and re. Okay? I don't know why. So the point is, when I consider G composed with F, what I'm asking is, let's see about what it does to do. First, you look at what F does to do. It sends it to A. So this is equal to G of A. And then you look at what G does to A, and it sends it to 1. So the composition forgets about this middle part and just says, take every element here and see where it shoots to over on the further set. And it's going to go exactly to 1. And now, let's look at what G composed with F of Ray is. Well, Ray goes to A. So this is going to be G of A. And then what is G of A? Well, it's just 1 again. So I've taken 2 different inputs, and they're forced to have the same output because 2 things getting mapped to the same point, G has no choice but to map this to the same point.
Okay.
And so so maybe this will help. The real picture for G composed with F is the following picture. I have A and I have C, and I have 1, 2, 3, and I have do and I have re. And the function between A and C called G composed with F sends do to 1, and it sends re to 1.
Okay, that makes sense.
Yeah, so the whole point is that composition of functions, I keep on drawing them this way because this is how to understand them. But when you just write it out starkly as a function, this is what it is.
Okay,
And
thank you.
it's not injective.
Right.
And the reason why it's not injective is because two different things are forced to go to the same place in the middle step. And then G has no choice but to send that to something. And then you just look at the boundary. Oh, these two things had to go to one thing.
Right. That makes much more sense. Thank you.
Yeah. Hmm. Great. Any other questions? I'm happy to be chatting with people about math. It's good. For question 7, for the function a, why did a have to be? So do you mean why is a required to be non-empty? Yep, sure. See ya. So Ben, what you've written is a little incorrect. No. Let A be a non-empty set. That's very important. So let me reiterate. What I wrote was no. So I want A to definitely not be empty. If I wrote it otherwise, then that's bad. But I think I wrote A is not equal to the empty set. I really hope that I did. Anyways, that's what's on the test. A is not the empty set. Right. So here's the point. Let me do a concrete example once again. Let's say A is equal to the set 1, 2, 3. There is a function f from the empty set to the set 1, 2, 3, which is just this vacuous, like trivial function which always exists from the empty set to any set. There's always a unique function from the empty set to any set because I'm just looking for a relation on the empty set. So are you satisfied with why there exists a unique function from infinity from the empty set to any set? Is that step okay? No, there's only one. Because what a function is a function. So when I fix A, there's only one. Yeah, you're right. If I change A, there is a unique such function for every codomain. But this question says, fix one codomain, how many functions are there? So I fix one codomain, then there's always a function from the empty set to any codomain, always. However, there is no function from 1, 2, 3 to the empty set because 1 can't be mapped to anything. And B, so here's the thing. So what you're writing with x to x squared is very valid when you're talking about like non-trivial domains and ranges. So for instance, when my A is equal to R and my B is equal to R, and I'm asking for the size of functions f from R to R, this is wildly huge. There is an unbelievable number of functions in here, of which x is one, or that is x maps to x is one such function, x maps to x squared is another such function, and there are mind-boggling numbers of other functions inside this set. But when you're dealing with, let's look at a different example. Let's think about all the functions from 1, 2 to a, b. Right? There's going to be one function that sends both things to A. There's going to be one function that sends both things to B. or both things to b. There's going to be one function which sends them right across, 1, 2 to a, b. And then there's going to be one function which sends them crossways, right? So from a set with 2 elements to a set with 2 elements, there are 4 functions. Okay? And all of these are secretly relations which satisfy some properties. For instance, this should really be thought of as being the tuples 1 comma a and the tuple 2 comma a as a subset of 1a, 1b, 2a, 2b, such that this set satisfies the additional relations that I need for a function. For every element in A, I've got a tuple in this subset such that it goes to something. And moreover, I can't map 1 to 2 different things. So if 1a is in here, then 1b is not in here. So are we okay with this idea of a function is? Yes, exactly, exactly. So when I'm looking for a relation, so I can erase all this. I can erase all this. Right, right. So all of this is, very deep and worth thinking about for a long time. Now we're saying, let's look at empty set 2a. Well, empty set cross A is just equal to the empty set. So if I want to find a subset of the empty set is a subset of the empty set, and then I have to check that it satisfies the additional conditions. And it does, when it's the empty set mapping to A. But when it's A mapping to the empty set, once again, A cross the empty set is equal to the empty set. The only subset is the empty set. But if A has elements, then it fails condition 1 and condition 2. It fails condition 1 in particular, because there are elements of A that aren't getting mapped to anything. There is no tuple 1 comma something inside the empty set. This tuple is not inside the empty set. But I need a tuple 1 comma something in order for it to be a function by this first condition. So the one case, the one remaining thing is that there does exist a unique function f from the empty set to the empty set. There's, no matter what goes here, there's always a function from the empty set to it. So if A is trivial, if A is equal to the empty set, then the answer for the first cardinality is 1, and the answer for the second cardinality is 1. But the moment that A has elements, if A has elements, then this thing is wrong, and the size is 0, because the elements of A have nowhere to be mapped to. So this is a tricky thing, and this is another place where probably this is not a good question to ask. It's interesting, and I did speak about this at length for like 20 or 25 minutes in class, but this isn't as important as some of the other stuff on the test, and it is just kind of tricky. So this is another aspect where this test was a little too tough. Yeah. But the point is to also, there was a homework assignment you gave back right before the test, and there were some issues with it. I forgot to email you about it. Is it too late now? I mean, kinda. Yeah, I'm gonna say yeah. Yeah. Whew. Yu Chen, what time is it? Are you still in the States, or are you in a very different time zone now? Hmm. All right. So, any last remaining questions? Great. All right. Have a nice afternoon, everyone.